Okay, so before the break, we finished up the stuff that was all preview mode. So that last thing there is probably something you're gonna do. And that thing we just looked at before the break would definitely be my recommendation for our class time tonight. We'll call it lab time, right? Hopefully you blocked off on your schedule until 8:50, but I'm not gonna talk for that long. That way y'all can go do stuff and learn that way, learn by doing. That's gonna be my recommendation is start playing around with getting some JSP pages together and seeing how to run the little bits of Java code that you've seen so far there. Because that's how we learn. It's a very active subject. We learn by doing. So let's talk about Java. I have some notes about the usage, kind of what computers are doing. Y'all have seen that before, right? Our central processing unit, different parts of that. The machine parts run through there. When we're programming, we're mostly working in RAM. Inside of the CPU is a piece called registers, and connected to the CPU is a piece called RAM. And they're technically separate pieces, but without a CPU, RAM is just a random chunk of squishy purple goo wrapped inside of black plastic to help it, because black helps dissipate the heat better. But it's, RAM is just a squishy purplish, clear, smoky purplish colored goo without a CPU to do anything on. So RAM is useless without a CPU, and likewise, without RAM, a CPU can't do anything. So they're technically separate pieces, but they always go together. And inside the CPU is a piece called registers, which, like RAM, is the volatile storage, our temporary storage, and RAM holds the current program we're working on, and the registers hold the current step of the program. So RAM is for the whole program, registers are one step at a time. But what's going on there is also very different than the code we write. What's going on there is like machine language stuff. If you're on, say, a 32-bit machine, that means the 32 bits refer to your register size. And that means any instruction you pass in can only hit, you're limited to 32-bit instructions. But those are 32-bit instructions at the machine level. So that's 32 bits of activate the ALU, activate register B, and, which components to activate or deactivate. So that level is very confusing. We don't work at that level. Machine language, right? A bunch of ones and zeros. Did I run in these notes? I had an example I thought was in these notes that I just pulled out, but I don't seem to see it. Is that the wrong set of notes? Nope. Let's write it down somewhere different. I had some binary and assembly and high-level language all put next to each other. But I used that in several classes. You may have seen that before. The binary is hard to work in. Very, very confusing. And even when we work in it, we don't deal with it the same way as the way it's written out. For one, I won't get into that. We're looking at a high-level language. It's hard to work with. So when the electrical engineers put a machine together, they include assembly language. That's a mix of binary and human readable keywords. A few keywords that we can work with, so like add, or result, or jump, or a few specific terms that we can intermingle with the machine code to the computer will recognize, but we're working with things that the human can deal with. Still really hard to deal with. So then we get to high-level languages, and that's where it's sort of more of a human form. It's kind of written in our language, like we think about it in the text file, organized top to bottom, left to right, which is not equivalent to what the machine runs. You always have to keep that in mind. You might write something that looks like one little bitty short line, but by the time that gets to the machine, it's 15 complicated lines. Or you might write something that looks like a big, huge, long line. If you turn it on, the text strapping would take up 5 5 or 6 lines in your text editor. And we get down to the machine level, it's 15 bits. So what we write is very different than what the machine runs. That's something we have to keep in mind, because we're going to work in that high level optimized for a human language that gets converted into something the machine can deal with. And later we'll talk about telemetry, taking measurements and stuff. There's a whole lot of that built right into NetBeans, so we'll see. Take a look at some of those tools later. But we're going to be working in a high level language and sort of putting things together in something that's a mix of words that we recognize, reference values we make up to our variables and method names, things that will make sense to us, mixed with some symbols and keywords the computer knows about. And then that will get translated into something the machine can run. Oh, okay, I know what's going wrong in Dallas. You have the development system, but you don't have the actual a Java virtual machine. The thing I was getting ready to talk about. Because, well, what we write in this high level language has to be translated into something the machine knows, which is going to be specific for the machine, right? So every machine is going to have different bits of registers, have different configurations of those electronics. So all the machines would know different things. So when they went to clean up C++ in the early 90s, that's one of the first things they wanted was something that could run anywhere. So that's one of the biggest things about Java is write once, run anywhere. We write the same code and it works on every machine because it's not actually running on every machine. So we write our code, we'll have our text file. Our usual first example is a hello world, right? That's the thing. And if you're looking at all the thumbnails on the screen, remember to go up in the upper right corner on Zoom and switch to speaker view. And you might have to double click on mine, but that way it'll be big enough you can see the board instead of that little bitty thumbnail next to everybody else's. So I'm just going to write hello.java. We'll probably do something better here very shortly, but the hello world program, we always want to run those because that's our configuration check, right? If we can print the words hello world on the screen, that means everything's configured correctly. And and we should be ready to do more. We don't want to do a whole bunch of stuff and then figure out that our computer's not configured correctly to run it. So we'll write our text file. Extensions are arbitrary, those are for the computer. The first part's for the human, the dot something's for the computer. We could call it whatever we want to do. We could call it a .txt file still, because it is a text file, and just tell the computer to compile it. And as long as nothing in there would crash the compiler, it would still be Java code. So the convention is to call it .java. Well, Java is a compiled language. So interpreted languages, we grab instructions one at a time. Grab the first instruction, convert it to something the machine knows, run it, then come back, grab the second line, convert it. So one thing about that is if you're doing it that way, your program will start running. It'll run through those lines until it hits an error. And then spit out what line that error is on and stuff. A compiled language, we take that whole file and turn the whole program into machine language or assembly language, or in the case of Java, bytecode all at once. We turn it into something the machine knows about. It's been many, many decades since the stuff we write in the text files goes directly to machine language. There's a lot of different levels in there that the machine still knows about. So we don't have to go all the way to where it's just pure ones and zeros in order to run. So we have to compile it. So from our text file, we'll go to a compiler. Let's see, I'll try to draw these things a little bit different, something like that maybe. So in our compiler, it's going to check syntax and other rules. So syntax would be like every opening curly brace has a closing curly brace. They come in pairs. Every instruction has a semicolon at the end. But there's other rules too. We can't say we have a string sort of data. I'll call it S1 and then put an integer there. That's different types of data. Java is a strictly typed language, which means it's going to run faster than an open typed or loosely typed language, because we reserve spots in RAM. So string might not be a good example. Let's talk about a different one. Let's say an int. That's our basic 32-bit integer. The binary code that you would have learned in your SDEV 120 class. So 32-bit signed integer. So we get a positive, negative sign. There's just 31 bits for a number. Some of those are going to be integer portion. Oh wait, integer, that's not double. Sorry, I drifted off into the next one already. An integer, 32-bit whole number with a sign. So we get the 1 bit for a positive or negative, 31 bits for the number. So we can hold a fairly large number there. I'll just write X on the board. Typing's easy, so in our code, we want to write something better than X, but writing on the board, I'll probably use one-letter things like math class. So we have this integer X, that's going to reserve as 32 spots, 32 bits in RAM to put that integer. So we couldn't put, say, a 64-bit double precision floating point number. We have multiple types of floating point numbers. One of the main fallback is going to be a double precision, 64-bit signed. So we have basically, you can think of that as you can cut the number in half. So 32 bits for the whole number portion and 32 bits for the fractional part. So kind of the equivalent of an integer. We have a 32-bit part for the first 32 bits are the sign and the whole number portion. But there's another 32 bits, so that's not going to fit in the spot we reserved for X here. So we have that kind of control, but that makes it go faster. The computer doesn't have to figure that out. So the compiler is going to check all those rules, the things it can notice. It won't notice everything. Sometimes things will compile that still have problems. But in general, it's not going to compile until you get most of the big problems fixed. And at that point, with Java, you'll have byte code. I'll draw a trapezoid here, or a parallelogram, whatever shape that is. I meant to draw a trapezoid, but we called this hello.java, but I pointed out we could call that hello.txt. We could give it whatever extension we want, as long as we tell the compiler to compile it and all of the Java code is valid. It will create a .class file. We'll make the hello.class file, and that's what's called bytecode. It's still a couple steps above assembly language, but it's something the machine knows how to work with. And in particular, the big thing with Java, looks like I'm running out of room on the board. I have two more symbols to write, so I'll come down here. This marker is trying to give out on me. Might not quite be gone yet. The thing that the first solution they came up with in the 90s to make one programming language that works anywhere is let's just use a virtual machine. So we install a Java virtual machine. the JVM. And from that error message, you just put in the cat a moment ago, Dallas. That's what's missing on your computer. So if you got to that error, that means you have the Java SDK, the software development kit, or actually Java, they call it the JDK, Java development kit. Most of our languages, we call it the SDK. But you have the stuff to write Java programs, and you have the compiler, so you can get all the way to here. But from that message you mentioned in the chat room, you don't have the regular Java virtual machine. So just the installation of Java to actually run the code once you do something with it. I will help you get that fixed after class. We'll track down the one you need. And then that virtual machine, it connects to the CPU. So we have one set of code that we put that virtual machine on any machine we have, and then we can run the same code on that virtual machine anywhere. So we don't have to adjust and write code different for our program to run on a Windows machine or a Linux machine or a Chrome OS, or we don't have to know what system it's going to run on and how to do that, or in some cases we don't have to know the exact motherboard that it's going to run on. We might have to, some cases we might have to make adjustments if we're going to run on a system with an AMD CPU instead of an Intel CPU, because those aren't the same device. They behave differently. So we want to avoid all that super complicated stuff, but still have lots of control. What they came up with was, let's just use a virtual machine. And then we have sort of the motto of Java: write once, run anywhere. We don't have to modify our code to do other stuff. And we don't, some of our other cross-platform languages, we don't have to wait for the computer to figure out what type of machine it is, which slows things down even more. So it still runs fairly quickly. So that was their first step when they cleaned it up. After that, they decided to go with like naming conventions and stuff. Naming conventions and consistencies, which we will see before long. We actually get a lot of power when everybody just kind of agrees to write our code the same way, follow the same naming conventions, and organize our stuff all the same way, even if it would pass the compiler and produce code that would run on the machine. There's extra power we get when we just follow those unwritten rules that we're all going to use camel case for our variables and Pascal case for our objects and spell everything out fully. For our getters and setters, which on a multiple choice quiz would always be accessors and mutators, we're always going to use the words get, then the variable name. Spell out fully, or set, then the variable name. Or in a Boolean, we'll say is for the getter, because that just makes more sense. It fits in a sentence, kind of the high level thing. Language saying, we'll see that periodically. And it's a convention, a way of doing things. We just all kind of do things the same way, and that's referred to as beans. We get a lot of power back from it. It also gives us some really nice ways to buy back the efficiency we lose doing object-oriented stuff. Because object-oriented stuff is good for the human. And what's good for the human is bad for the machine. And what's good for the machine is really hard for the human. So there's always a trade-off. Java is solely an object-oriented language. We kind of had to see that on the very first thing we looked at. So we're always dealing with object-oriented languages, and we lose efficiency when that happens. So it's nice to have ways to buy those back. And that there's a really nice one with in Java that flows from beans, those conventions that we all just sort of agree to do things the same way. So that's our general flow of things. We'll look at some bytecode. We have, so starting off here, I put up here, we have to say what sort of data we have. And that's what an object is. If you haven't seen that before, just started getting introduced to object-oriented programming, it confuses people, sometimes confuses people at first. They want to compare it to like methods or things, but an object is a data type. So like the same way I declared this integer X, if I made something called my object, I would declare it that way, my object Y. It's a data type, so it gets categorized with integers or double precision floating point numbers, or some of the other ones, which I should probably make a list here. This way. Which we'll start with our primitive data. We do have some built-in objects we can use, but to start with is our primitive data types. This is just the basic, the most basic type of data. We can't break it down further, such as our integers. We have a bunch of them. So the first one is definitely the one you would have seen in the SDEV 120 class, the byte, an 8-bit whole number. It's going to try to do an unsigned one. So if everything's positive bytes, it's going to use 8 bits for the value. But then if you start using negatives, you'll have to adjust that a little. But 8 bits. So our just smallest data type. And if our numbers fit in that, we're not using as much RAM, right? Anytime we can use less RAM, that's computer resources that can be used elsewhere. Because not only is it what it takes to store in RAM, it's how much of the registers does it need? How much of the arithmetic logic unit or floating point unit in the CPU is it going to use when it processes? Right? If we have a 64-bit machine and all of our numbers that our program uses could fit in bytes, then we can fit 8 bytes on each pass. So we can do we could do way more than we could if we used all integers. Because it's not like it doesn't go to waste. Like if we have 64 bits passing through the ALU, the piece that actually does the 2's complement math, but we can pass 2 things through there at once. So there's plenty enough bits to do that. The computer can keep track of it. A human would certainly get lost even trying to diagram it out, but the computer has no problem with it. So we want to put thought into things like that. You don't want to just throw out a number and work with it, because anytime we can save stuff and work with smaller data types, that's going to translate to more speed. That's the one people are interested in. There's lots of things there, but speed is the one we care about, right? How fast does it get done? Which machines are very, very fast these days. A point I already expressed a couple times. Remember, Java is for big things. So for example, here in Louisville is Humana's main headquarters. 40 floors of people filled there, but Humana is huge, right? All across the world, that insurance company has all those agents all over the world. So we're not talking about small programs. We're talking about enterprise systems with 50,000 employees and 10 million clients all trying to access that software at the same time. And in that case, even a little bit adds up, right? If we save 8 bits on a number, and then 50,000 people need that number at once, how many bits? We can punch that in a calculator. That's a lot of bits saved right away, just on that one little spot. So Java is for big things. So those efficiencies and things add up quickly. Think of Humana, 50,000 employees and 10 million customers that might all need to access that software at once. So it's not like one person's going to do it on their machine. Things add up. Our next biggest size of integer is a short integer, 16-bit integer. Then we have our int. That's the one we're probably going to fall back to the most often. I should put on here 16 bits. An int is a 32-bit. Then we have a long, which is our 64-bit integers, so that we can hold bigger and bigger numbers. And if you need a number bigger than that, we'll see it. It'll be later in the semester, but we also have big integers and big decimals, which are actually strings. So we have our number as a in Unicode, and then we calculate the value of each place at runtime. So if you did things like go to that site on the internet and download pi to a trillion digits, a 64-bit integer, 64-bit number is pretty big, but that's not going to hold pi to a trillion digits. Well, that one's an integer. We have a floating point one's equivalent, but that's a really, really big number, right? There's a lot of bits there. So we just store that as a string, and then we calculate each digit at runtime. We will see those later in the semester, because they're definitely not primitive data. But that's our integers. Am I still on the screen? Okay, yeah. Well, then we need to have some floating point numbers as well. Two big ones, the double precision floating point number, or just a float. Double is a 64-bit floating point number, 64 bits, and a float is 32 bits. So saving 32 bits each time we can use a float instead of a double. So on that example that I was falling back to, the rough numbers from Humana, 50,000 people, or 50,000 employees, just under 50,000 employees, plus just over 10 million customers, 3, 4, 5, 6, and if we can save 32 bits on each number times 32, adds up to let's see, 1, 2, 3, 4, 5, 6, 321,600,000,000 bits pretty quickly. Billion, that's gigabits. So we're saving 321 gigabits, which would translate back into speed. So that's everybody trying to access it at once, obviously, but the numbers grow very, very quickly when we're talking about enterprise size systems. The stuff we hope to build, because those come with great big paychecks, right? If we're building for a company with that many employees, we're going to expect a paycheck that's appropriate for it. Double and int is kind of our fallback. For some of the others, we need to say something. So if we have a long, you do have to add an L at the end. I'm going to write it as an uppercase. It can be uppercase or lowercase, but a lowercase L looks like a 1, so that's going to be confusing. And a float, you have to add an F at the end. It's going to try to make it a double. So if you wanted just the simple version of pi, 3.14, as a floating point number, because you're only doing 2 digits or something, you would write 3.14F. And that specifies to the machine that it has to always use a floating point number for that instead of a double. If you leave the F off, it's going to try to make it try to use it as a double. Let's see, floating points. Then we have Booleans. Float. Then we have Booleans, which are 1-bit Booleans. So 1 bit for true, 1 bit for false. 0 is false, 1's true. That's probably what you expected on that one. It usually takes more to store the variable we put that in than the data itself. But we want to put it to a useful name. Right? Typing's easy. It usually takes more to store the variable for the Boolean than the Boolean itself. Characters are primitive data as well. So char with and notice these are all lowercase. It's kind of hard to tell in this. That is supposed to be a lowercase s. So all of our primitive data starts with a lowercase letter. A char is a character. So single quotes. And it's equivalent to an int. Equivalent to an int. So it's like reserving spot for an int, only a special case of an int. It's going to be processed as a letter. But we can also use it as a number. We will see that very soon too. Probably not tonight, because as we talk about this, we'll want to start doing some stuff. So that's our primitive data. Everything else is built up from that. Thus, I just expressed the point that those are all lowercase letters. Did y'all notice in our examples already that when we did a string, I did a capital S? So a string is an object. A string is an array of characters. But it's a common enough one that it's included, and generally we think about that as one of our primitives, but technically it's not. Technically, it is an array of array of one of our primitive types. And then we can use that. We use our primitive type to make our more complex type of data, our objects that we're going to work with. That's our starting point, though. We have to, and when we're writing in Java, we have to explicitly say what type of value we have, and then the number, sort of the Java syntax. Let's say it in an example. It's an active subject. That's probably enough talking, right? Let's do now. So I'm going to create a new project. We're going to do everything in projects. So new project. I'm just going to do a regular Java Ant project. Should we do it? Yeah, I'm going to do a regular main one. We looked at JSP pages earlier. I'll try to switch back and forth because main, we'll still use the main method some, but in our modern world, we're much more likely to use the stuff on the server. So I'll create a new Java Ant application, give it a name. I'll call this primitives. Because this one I'm going to put on the GitHub here in about 10 minutes. Create that. There's a template. It stretched out a little bit further than I thought. I was wanting to look at changing the template today, but we'll look at how to change that starting template soon. Our Java docs and to-do comments, which are very, very useful. So I want to use those, but they're in our main method, which at least at the beginning, type that out. I'm going to get it memorized. It needs to be accessible, so public. It's our starting point. We don't have any objects created that we can use to access things. So it has to be static. That means there's one and only one copy. So static is, if there's only one copy, we can look at the design for the object instead of an instance of the object. We look back to the blueprint. We look at the class file, the class definition when it's static. Doesn't return anything when it's done, or the return type is void, which actually is a primitive type of data. Void doesn't mean nothing. Void is a data type. It should probably go on this list, but there's nothing else to say about it. It's the emptiness version of primitive data. If you know a little bit of electricity, void and null are less than 0. That's where we let the electricity floating. It might be zeros, it might be ones. Don't pay it any attention because anything there is just random gibberish from the fluctuations in the electrical circuitry. That's what void and null are, which is a type of data. But we consider it nothing when we're thinking about our algorithms and planning our algorithms. So, we'll just start with the type, going through these. So we have our byte data is our smallest one. And the Java syntax, we say what type of data we have. Give it a reference, I'll call it B1. And that's going to be a new byte, or we just put a value here. So 8 bits we can hold, should be able to hold from 0 to 255, right? So we'll just throw a number in there, 123. And then I'll come down and system.out.println, which in NetBeans, if you type S out and then push tab before you hit space or anything, it'll type all that system.out.println. Let me do that again. If you hit the end key, it'll put your cursor at the end of the line. And before the days of mouse, if you haven't seen this, we would hold shift and use the arrows and the stuff to highlight. So if you use the end key, put your cursor at the end and then hold shift and hit home is a really quick way to highlight a whole line. And we take that out and S out and then push tab, we'll do the system.out.println. So we don't have to type that whole thing every time. Most of your IDEs will do that. There might be some variance in it, depending on the particular one, but it's just parsing the string. Since we're a programming class, if you ever write something like that, all you're doing is parsing the string. You look for S out, it's like, oh, that's not in the language. It probably means system.out.println, and replace that in the text file we're writing. And then I'll print B1. So save that and give it a run. And see, we get our output there. That one fit. What if I add a 5 in there, 1523? I would already underlined it. I was going to ask about this. I probably should have done that in text editor. That's not going to work though, right? I haven't even looked at the error message yet, but I see head shaking no here. And y'all know what's wrong with that, right? 1,523 will not fit in 8 bits of data. So whatever our type is, we need to keep that in mind. A short, it would work in there. S1 1567. We don't get any sort of underlining on it. I should add some labels here. 8 bits of data to store plus that B1 and S out. And short is the next size up, a short integer, so 16 bits of data to store plus S1, which in 16 bits, 1,000 something will fit. But once again, we'd have that same problem with a couple more digits. I think I have to add a couple more this time. Yeah. So if I tried to make it 144,000, that's not going to fit in 16 bits. What is 2 to the 16th? That's 2 to the 8th is. I have a calculator out already. Already pulled it out of my backpack for something else. 2 raised to the 16th is not one that I have memorized. 65,536. Oh, I did have that number memorized. Which 0 is one of our values, so actually we can go up to 65,535. So if our number is smaller than that, we can use a short and save a few bits off an integer. So most of the time we're going to use an integer. So 14,000 would fit there. And once again, we say what type of data we have. Give it a reference value. I'll say I'll just call it I. Because I want that one doesn't look very useful next to the I. So integer, well, any integer, 145,678 will fit there. It's a 32-bit integer, so we can get quite a bit bigger with that. 65, 2 raised to the 32 is Pretty big. 2 raised to the 32nd power. 3. So 4 billion, just over 4 billion. So quite a bit bigger numbers than we fit there, and going up to 4 billion, but its ends are signed. So cut that in half. Half of them are negative because we have to use that leftmost bit. Our biggest bit is reserved for the sign. So still a couple billion numbers to get fit there. So quite a lot, and it's a 64-bit number. So you'll notice the pattern. Sorry, 32-bit number. 32 bits of data to store plus pi. And notice how there's no need to cast it or anything to change our data type to fit in the string. I'm just concatenating right in there, and Java has no problem with that. Then along, if we have a really big number, let's fill this out. Yes.
If we wanted to add a period after the variable, you just put the plus, quotation marks.
Yes. So we just add some more stuff afterwards. Plus dot, like that.
Yeah.
Yep, just add some more stuff afterwards. I'm going to call this big. So along has is for much larger numbers. 3, 4, 5, 6, 7, 8, 9. 8, 7, 6. All right, there we go. That's something definitely too big to fit in there. But notice how it's still underlining it. And when I hover over it, it says integer number too large. Because that's what I put here on the board. It's going to try to make it an integer. If we just type a bunch of digits. We have to add an L to specifically say we have a long number. Sort of a remnant nowadays. Most machines are 64-bit machines, but well, on a 32-bit machine, that's an easy example. On a 32-bit machine, our registers were 32 bits. Our arithmetic logic unit was 32 bits. So if we needed a 64-bit number, that means we had to do two instructions to do it. We do the first half, and then the second half would have to be a completely separate set of instructions. At the machine level, it's one line in our code. So we have to specifically say we want the long. So a lowercase L works. It's that L in the F is not case sensitive, but a lowercase L will look like a 1 and throw you off on your code. Give that a save and S out 64 bits of data to store plus big. And when we run that, which is F6, if you just want to hit a button instead of going up and clicking the thing with your mouse, F6 will run it. And if you have multiple things going on, Shift F6 will run just the file you're looking at, as long as it has a main method in it. It does have to have a main method in order for that to work, because we can only start at the main method. Doubles are similar. We're going to generally use doubles unless we need to save space. Anymore, not many people other than game developers use floating point numbers. So if you're doing it 140 times a second, if you're doing lots and lots of math 140 times a second, those 32 bits do add up very, very quickly, especially with lots and lots of stuff going on in your game. So game developers use floating point numbers, but otherwise pretty much everybody uses doubles. I'll call it dub, and that's going to be an integer. I'll do that. That's out a 64-bit real number, I'll say that. Plus stub. And when we run that, oh, I forgot a space, but nothing too fancy on that one. I did some division here though. Say 4 divided by 3.1. I should do something that would kind of come out even. So if we did 12.0 divided by 3.0, should be 4.0, right? Well, that one came out as 4.0. It's gonna, I guess, Java is gonna adjust, the new Java virtual machine is gonna adjust. We have to be careful with the exact values. You remember learning binary code, and when you start doing the fractional part, we have different values than the tenths that have to add up. If we have 32 bits that we can use for that fractional part, it doesn't necessarily mean it's going to come out evenly. 1.07. I often like to ask homework questions about sales tax in Indiana. $1, and I'll ask you to do a $1 item because your program will probably say that wrong. 0.07 in binary will repeat forever. So we never have enough bits to write 1.07 evenly in binary. It's really nice in base 10, but not in base 2. So we have that little discrepancy. So way down the line, our number might not exactly come out evenly for what we're thinking about. So the big thing there is when you're doing selection structures, which I thought we were going to have time to talk about quickly tonight. Way down the line, equality might not hold. One of them might select 2. If we have 3 as a double number, we might have 2 versions that we think should be equal, but when we go to compare them, and if we say equal to, one of them might be 2.999999999, and the other one 3.000000001 way down there. So they're both 3, right? A little bit way 30 decimal spots over doesn't change those are both 3, because as soon as we start doing any rounding, they would be the same. But the computer would not count those as equal, right? Because they're different. So you do have to watch that and be careful with that. That's kind of across the board programming. It was probably carefully avoided in your introduction classes to avoid hitting that problem and just confusing you to no end. But it's something about machines we have to watch out for. The big thing is just don't check exact equality with floating point numbers. You always want to do less than or greater than or some roundabout way to check that equality. Because of that last little bit there at the end. Then a float is like a long float. FLT 1.07. But again, that same error message. Incompatible type. Or this one's a little bit different. Lossy conversion. So it's going to try to default to a double, which is 64 bits. 64 bits will not fit in 32 bits. We could go the other way. If we had a float, if we had something 32 bits long, we know 32 bits will fit inside of 64 bits easily. So we just have a bunch of extra zeros somewhere. But it doesn't, it only goes one way. 32 fits in 64, but 64 is not going to fit in 32. So we do have to explicitly say we have a floating point number. And just tack on an F at the end to make sure you want to tell the computer, save those 32 bits. Kind of like the long. I'm gonna stop printing those just to quickly get these out here so you can start doing stuff with it. Boolean, I'll just call it flag because that's what we're going to use it for. And that's either going to be true or false. lowercase letters. Boolean other flag is false. I was write them out there. All lowercase letters. I know the prerequisite classes for this all use Python anymore, so everybody would get used to that. Had that capital letter at the beginning drilled into your head. So in Java, lowercase. It follows our camel case conventions. Then a character, char. A lot of people just say char because that's going to be abbreviated. Kind of like integer, we abbreviate it, so people just say int and char. Is a single letter. So start of alphabet, and the Java convention is spell everything out specifically. Spell it out. Don't be lazy with typing. Typing's easy. And be descriptive in your variable names. And then for a single character is a single quote mark. So our alphabet starts at A. And notice if I switch these over to double quote marks, it's going to give me an error message. String cannot be converted to char, which again is a downgrade. A string is a collection. It's a huge array of characters. So we can't take an array of characters and squeeze those down to a single character. Going the other way would be okay. We can take a single character and shove it into a great big array. So then we just fill everything else up with zeros or null values. And there's no problem with that. But single and double quote marks are not interchangeable. So you have to watch that. So that's our primitive data type. And you probably want a string in there. We saw, whoops. Control Z is still undoing netbeans. String, we almost count that as primitive data, but it is an object, so in uppercase S, capital S on string. Some words. Hello world, I guess I'll just throw the standard example in there. So double quotes for a string and single quote for single character. That's kind of what we would think of as primitive data. So we're going to build all of our programs from that. That's the basic data types we have to work with. And just like how string is there, there are already a lot of objects built that we can work with, and we're going to build our own objects. But we combine those into more complex data types, which is actually what we're doing here. We're making a more complex data type. We're just not going to do anything with this one. So that's the primitive type. We'll look at selection structures on Thursday. Down to 55 minutes left in class. I want to make sure there's plenty of time to do stuff. Last little note, remember things in this class are going to be submitted on GitHub. So you want to set up a repository, however you feel like organizing it. Let's add a file. Upload a file. There's a 100 file upload limit. So if you use the web app one, so we should be under that limit for anything that fits in the time constraints of the classroom. I don't think we're going to write over 100 files or anything. Your final project might be pushing it because of all the automated projects, all the automated files, but you'll probably be okay to use the web thing for this. I'm going to cancel out of this. If you want to create a folder, we have this whole NetBeans project with all this stuff. It's like, well, the only thing I did is source code. I don't want to upload all that automated stuff. I can have the computer re-automate that. To create a folder on GitHub, if you haven't seen that, you want to go to create a new file and type in the name of a file, but include a section for a folder. So new folder / another file. I'll just make it .txt file. So when you type in that name, notice it extended that out, and that will automatically create a new file. This is a scratch thing, so I'll just make a note to delete this later. Just don't really need this, just needed it to create the folder. So now there's a new folder where I can upload things to. So over in that new folder that was created, can add file and I'll get the Zoom thumbnails out of the way. Just drag and drop the stuff, that one file over. So from primitives and the source folder, there's a primitives package. So we would, if we went to import it, we'd need the package name. So we would import primitives with a lowercase dot primitives with an uppercase D. So that's our import lines, how those work. And then just drag that one file over instead of all of the files. Or maybe just drag your source files over. Because that's all we really need to create it, right? Everything else is automatic. Or the compiled version, we can recompile the source code. All the automated stuff we can redo. So all we really need to store is our source files. So send me, make sure you send me the source files. You can upload the whole project if you want, but over the years I found because of updates and things like that, I found it's a lot better just to store the source file. Just store the source code because that's the only part we really need to save. Everything else is either automated or can be redone when needed. But stick it on GitHub, and then for your homework submission, you would just send me the link on GitHub. Which actually, I'm going to download the whole repository. So wherever it's at, you can just send me the main repository link. That's how you will submit stuff. But we need some code to do stuff. So the math, like you would have expected it, I'll put it as a comment here. The math, add, subtract, multiply, integer division. I should probably do one with the division. Modulus, and that'll get you some stuff to start doing. Division. So we have a couple integers, X and Y, and notice I just declared them. I didn't assign anything, but you can declare a whole bunch of integers at once, or a whole bunch of doubles at once. Double W and B, some math class variables. Please use better variable names. I'm just trying to rush to the end here. And then when we divide it, so if Z is X divided by Y, oh, we have to assign those first, don't we? Then we can assign values. So like X is 4, Y is 3, W is 2.34, V is 5.76. And then when we divide things, I'll just print them out here. Print out X divided by Y. Print out W divided by V. And print out X divided by W. So notice when we did 4 divided by 3, we didn't get the fractional part. It's integer division, so use modulus to do quotient and remainder, are more accurate division anyway. Floating point division gives us a floating point number, and down here we had an integer and a double, so it's going to default to give us the floating point number. So if you want floating point division, but you have integers, so like X is 4, if we divide it by say 3.0 instead of 3, there's now a double in that, so it's going to go back there. So if you want all the decimal values afterwards, make sure you're putting a decimal in your division. If you want fractional part, include decimals. I'll save that and upload those changes to GitHub so y'all can see that example or download it real quick. GitHub, so mine's Francis-Chris5 and then /SDEV 200-fall 2022. Hopefully that name's not all lowercase. Hopefully the name's not too difficult to remember. Then in a new folder, I'll move the Zoom stuff out of the way and upload that latest version. So if you want to check an example, our class examples will be loaded up there. I was hoping to get to selection structures tonight, but I'm more concerned with making sure there's plenty of time to play around with that. So you all can start doing some math, printing out results, getting some input. Really, my big recommendation would be to maybe do that on a website. Oh, I can do casting here as well. Maybe do one more here. S out. An alternative is X divided by Y, but we want that floating point one to cast to a different type. You put the other type in parentheses right before it. So it's embedded in there, but does everybody see how that's working? So X, and then right before X, double is in parentheses, and that turns X into a double. So that one will also give us the one. That way casting is included somewhere, and you can see all those examples at once. So I'll upload that in a moment. So start playing around with stuff. My recommendation would be to play around with the JSP pages and get started with that, because that's probably the one least like anything you've seen before. But also some math. There's examples in the textbook. It's an active subject. We learn by doing. So now's the time to do stuff. I will be sitting here waiting on questions until our scheduled time ends at 8:50. Text messages and Ivy Learn messages are the two things that make noise on my phone during the semester. So that's the quickest way to get a hold of me. You can ask me questions anytime, but right now is when I'm going to be sitting here waiting for questions to come my way. Does anybody have any questions before we wrap up though? Okay, so that'll hopefully get you some stuff to start with. Some basic math, do that basic math with the HTML forms on the JSP pages. And I'll see y'all on Thursday, and we'll get into selection structures and loops. The syntax for it, because you already know what to do with them once you already know how to put algorithms together with them. We just need to see the syntax for it in Java. See y'all on Thursday. Let me know if you have any questions. And let's take a look at that, Dallas, and we'll get yours up and running. Stop the recording.